Hello guys, so this is the third part of lecture 6 and our second example. So in the first example, we solved our first circuit or make our first circuit analysis in that course for a circuit in which it has a diode connected in a forward bias. Forward mean positive terminal of the battery of the source is closer to the B side, negative terminal of the battery of the source closer to the N side. Here we have another example. Now we have two diodes in our circuit. Okay, of course that will make the circuit analysis more complicated, of course. And remember, it was already complicated because of the nonlinear relations, and to solve the nonlinear relations. Now imagine a situation if you have two. This, of course, will add another one nonlinear equation. So if you have one diode, you will have one nonlinear equation. If you have two, you have two nonlinear equations. Three, you have three nonlinear, and so on and so forth. It's really complicated. Okay, but let's see. Let's see how we're gonna overcome such thing. Okay, we have here two diodes, D1 and D2. The first thing that you should do all the time, to check first if they are connected in, each one of them forward or reverse. Okay, so let's see. Here they are both back to back. Okay, so both either should be forward or both should be reverse. They are in series. Okay, let's see. So the positive terminal of the source here is closer to the N of D1 and the N of D2. Okay, and the negative terminal of the source is closer to the B side of D2 and also the B side of D1. You can just interchange them because this is in series. You can draw D1 in bottom and D2 in on the top here. Okay, because they are in series. Or you can say we know forward and reverse based on the expectation for the voltages of the N side and the B side. Okay, so basically this node here in this circuit has higher voltage than this node, the ground. Okay, so we expect that this node to be higher voltage than this one, and this one to be higher voltage than this one. Okay, again, this node we expect to have higher voltage than this node, so D1 is reverse, and D1 and this node we expect that it should have higher voltage than this node, which is the ground. So again, D2 is reverse. They are for sure they are reverse. Okay, so by just the first look here, D1 and D2 are reversed. And that's very important to know. Okay. Both, according to the equation, both diodes have a breakdown of 100 volt. So if the reverse bias voltage reaches minus 100, they will break down. But I01 or IS1 is only 1 microamperes, and IS2 or I02, the reverse saturation current, is 2 microamperes. It's bigger, double. So roughly, we expect that the characteristics of VD2 to be, or diode 2 should be something similar to this one. With double here, the reverse saturation current, 2 microamperes. But both break down at the same voltage, minus 100. Now, how to solve that problem here? Okay, so let's go back to our, color. So basically, we do what we used to do with just normal circuit analysis. We write equations. So our first equation here is always think about KVL and KCL. KVL or Kirchhoff voltage law, KVL. Okay. So basically, This is V input. This is the direction of V input. This is the direction of VD1. This is the direction of VD2. From N to B. So basically here, from KVL, V input plus VD1 plus VD2 equal to 0. And remember, V input here is 90 volt. It's a given. 90 volt. This is 90 volt. Let's write it here. Okay, this is one equation in two unknowns, VD1 and VD2. Good. We know from diode 2, or let's call it D2, ID2 equal to IS2 or I02, whatever you call it, exponential minus VD, I'm sorry, VD over VT minus 1. This is another equation, but we have another unknown now, ID2. So this is ID2 and VD2. So we now three unknowns. From D1, ID1 equal to IS1 exponential VD1 over VT minus 1. This is number 3. And we have another unknown now, ID1. So we have three equations so far with four unknowns, ID2, ID1, VD1, VD2. We still need, another equation. So you guys just pause this video and give yourself a minute or two and just look at this circuit and try to guess what should be the fourth equation. I'm gonna count to 5 and resume. So what you just pause? 5, 4, 3, 2, 1. I think you guessed it and guessed it right. It is KCL. Basically here this is I, this is I D1. We always assume the current flowing from B to N. And this is ID2. Basically, ID1 and ID2 they are in series. So ID1 is equal to ID2, equal to I, for example. So the force from, let's write it here, from KCL is this time, ID1 equal to ID2, call it I. So I equal to. So we have now three equations in three unknowns because I is just ID1 and ID2. So we have now three equations in three unknowns. But it's not over yet because two of them are nonlinear. Okay, two of them are nonlinear, which is really, very complex because now you get VD1 in from equation 3, you get VD1 in one side and the rest in the other side. Then you take this VD1 and put in substitute in equation 1, then VD2 again in equation 1. It will be very long equation, okay, that has only one unknown, which is I. But it will be really hard to solve. Okay, you can of course use iterations, but you see, it's not when you increase the number of diodes, it becomes very complex. Maybe for two, still doable, maybe, but it will be error prone. It may have longer iterations. I mean, in the last example, 3 iterations when we get the solution. And if you try to draw it graphically, it will be also complex because the equations that you're gonna draw, which is equation 1 after substituting by VD1 and VD2, will be also complex. Okay. So we need a smarter, solution than this. This is still valid. Okay, and maybe doable, as I said, with two unknowns. I'm sorry, with two diodes. But we need a smarter solution, and that's why I draw in the first place, the two characteristics, sketch the two characteristics of D1 and D2, diode 1 and diode 2. Okay, let's think for a moment. The first thing we did here is that we analyzed that, or we analyzed our circuit and we discovered that D1 and D2 are reversed. So basically we are working in that region. Let's get the, so we are working in here in reverse. D2 is reverse and D1 is also reverse. This is what is the connection of the circuit is telling us. Okay. So maybe the operating point, and I mean by operating point ID and VD of each diode, maybe here, maybe here, maybe here, maybe here, maybe here in the breakdown. Nobody knows. This is our job now to do. But we know that D1 and D2 should be reversed. We know another piece of information, that ID1 is equal to ID2. ID1 is equal to ID2. Okay? And this is very important information that we're gonna use afterwards. In reverse, we have three possibilities. We have three possibilities. So let's talk about, for example, D2, because it's much bigger, range. But what I'm gonna explain for D2 is also applicable for D1. We have three possibilities. That D2 is working in that region here. Let's call it region 1, in which VD as a magnitude and VT are comparable. Like, for example, VT is 0.026, okay, or 26 millivolt. So VD may be 50 millivolt, or 25, or 20, or 10, or 40, something comparable, a little bit less, a little bit, higher than VT. Or maybe in number 2, region 2, in which VD as a magnitude again is much larger than VT. Or maybe in breakdown, let's call it number 3. If we are working in region 1 and region 2, the equations, the exponential relation are valid, which is ID equal to I naught or IS exponential V over VT minus 1. If we are working in the breakdown, this is even easier, because if we are working in the breakdown, then we know VD for sure. It will be equal to minus VBD, which is 100. So, for example, if we discover that D1 is in breakdown, then VD1 for sure is minus 100. And we have one of our unknowns now is become a known variable. And again, the same for D1. D1 might be here in region 1, or might be here in region 2 before breakdown, or might be in breakdown, region 3. So let's write down all the possibilities. Okay. So we have two diodes. Let's go back to our favorite color. We have to, let's do that in a side here. We have diode 1 and we have diode 2. So possible, let's do that in another color. Possible operation, reverse operation, reverse operation. We might be in 1 or 2 or 3. So maybe diode 1 in 1 and diode 2 also in 1, region 1. Maybe diode 1 is 1 and diode 2 in region 2. Maybe diode 1 in 1 and diode 2 in region 3. Maybe diode 1 in 2, diode 2 in 1, region 1. Maybe diode 1 in 2, diode 2 is also in 2. Maybe diode 1 in 2 and diode 3 in 3 and diode 2 in 3. Maybe diode 1 in 3 and diode 2 in 1. Maybe diode 1 in 3, diode 2 in 2, diode 1 in 3 and diode 2 in 2. We have no other possibilities. That's all of them. Okay? So why I am putting down these possibilities? Because this will be our philosophy from this point forward. Dealing with diodes are really complex. It's not easy, especially that because we want to avoid using the exponential relation. Okay, so we will gonna use our mind and think a lot about the circuit, try to guess which operation, which operating point, which region the diode is operating in. For example, I will make it close for you now, guys. For example, if we assume for a moment that this is the correct assumption, that both diode 1 and diode 2 are working in their region 2. Let's see if this is valid or not valid without even solving, just by looking at the characteristics. If we assume that diode 1 and diode 2 are working both in region 2, here I mean. So let's assume that diode 1 and diode 2 are both in region 2. Okay, I'm gonna work with this assumption and see what kind of destination we're gonna go to. If we assume that diode 1 in region 2 is in ID1 for sure equal to minus IS1, which is 1 microamperes. If we assume that diode 2 in region 2, so ID2 equal to minus IS2 equal to minus 2 microamperes. Remember here that ID1 must be equal to ID2 because they are in series. So that's incorrect or invalid because D1 and D2 are in series and ID1 must be equal to ID2. So that assumption here is not valid, is wrong. And that's the idea to solve it. We're gonna, think a little bit about the circuit and try to guess one of these operating regions. Okay, maybe from the first time it will be hard, but most of the time, 90% of the from your second guess, it will be valid. Actually, 70% of the time it will be from the first guess, or 80% even. Okay, from the first guess that we're gonna guess from the first time the correct assumption, the correct region, we can say, for D1 and D2. Okay, so let's go back here to our circuit and see which one of in these two are right or close to right. Or we're gonna assume one of them, then we go with the solution. If we get valid something that is matched our inputs, our givens in the example, something that is that is right, correct, then this is the correct assumption. If we assume, if we are unlucky and assume something invalid, like assuming that D1 and D2 are both in region 2, then we're gonna get something invalid. Then we're gonna cancel this assumption and assume another one. Okay, so let's look here and see what should be the correct one of them. Okay, let's see. So basically here D1 is so restricted because D1, so basically here, before that, basically here, okay, let's look at the circuit now, okay, and look at the breakdown. So the breakdown voltage for both of them is 100. Is 100, okay? Remember, our diode is a passive circuit. It's an element that needs a source to give it its voltage drop, okay? And remember also, you cannot have an element in your circuit that has larger voltage than the input, okay? So, in order for D1 and D2 to go into the breakdown region, the input must be larger than or greater than or equal to 100. But our input, V input, is only 90. So we will exclude all the cases in which one of them or both of them are region 3. So since V input is equal to 90 volt less than V breakdown 1, which is equal to V breakdown 2, which is 100. So we're gonna cancel all the assumption in which one of them or both are in breakdown. So we're gonna basically reject this assumption, reject this assumption, reject that one as well, and reject that one. Because these last three, two of them, D1 is in breakdown, but it can't be in breakdown because it needs a voltage, it needs a bigger source. The last one is for sure because both are in breakdown, so, and you can't have such thing. And also this one and this one. To make you guys feel more comfortable, let's assume, for example, the last one. So let's assume, so let's continue this first. So no diode should be in breakdown. To make you guys more comfortable, let's assume one of them and see what's gonna happen. So assume that diode 1 and diode 2 are in breakdown. So if we assume so, which is this case here, so VD1 for sure minus 100, VD2 for sure minus 100. Let's do Kirchhoff voltage law. You know that V input plus VD1 plus VD2, if you look at the circuit, you'll find that all of them are in the same direction. So you know that KVL should give you zero, but let's see the case here. This is equal to 90 minus 100 minus 100. This is basically 90 minus 200, which is minus 110. This doesn't equal to 0. So KVL is violated. So it is incorrect assumption. So if you didn't just think about, that the V input is less than 100 and you just by mistake assume that any one of them is breakdown, you will get something like this. You will see that KVL is violated. If you assume just one of them, you will, again, no problem. If you do, you will reach some other incorrect, fact, we can say. Now what we're gonna do? So let's now look at the assumption. Okay. Number one. Assumption one here, that D1 and D2 are both in region 1. Both in region 1. Here and here. That means that VD1 and VD2 are, comparable to VT. In millivolt, we can say. That's also incorrect assumption, because basically, let's assume it's, 1 VT. So VD1 is equal to 1 VT, VD2 is equal to 1 VT, or minus VT or minus VT. So both addition is minus 2 VT, then Kirchhoff is also violated. It will be 90 minus 25 millivolt minus 25 millivolt. It's also violated. Even if you assume 10 VT, which is really big, it will make you to work in region 2. 10 VT means 0.26. So 90 minus 2.6 minus 2.6. I'm sorry, 90 minus 2.26 minus 2 minus 0.26. Again, KVL is violated. This is not equal to 0. This is KVL is violated again. So it looks like the first assumption is also not valid. How about the second one? So this is also not valid. You can do it in details. Okay. So looks like we have only 2 possible assumptions. Okay. I know the solution. The solution would be that D1 in region 2 and D2 in region 1. This should be the correct one. And this should be also incorrect. But, to teach you more how to assume and reject, let's assume that D1 in region 1 and D2 in region 2. So let's assume. So we end up canceling this assumption. We end up also canceling this assumption. Let's assume another bad assumption. Assume that D1 in 1 and D2 in region 2. If D2 in region 2, then ID2 equal to minus 2 microamperes. Minus IS2 minus 2 microamperes. And that's a problematic. Let's see why. Okay. We said that D1 is in region 1, right? D1 in region 1. That means that ID1 as a magnitude is less than IS1. Let's look back here and see. If D1 is in region 1, then this is its ID. It should be from 0 to minus, its maximum would be magnitude IS1. It can be, for example, minus quarter microampere. It can be minus half microampere. Its maximum is minus 1 microampere. So it should be here, one of these points, which all of them as a magnitude less than 1 microampere. Okay, so ID1 should be less than 1 microampere because D1 is in 1, right? But we know that ID1 should be equal to ID2. So from that, ID1 is equal to minus 2 microampere. Now the magnitude of ID1 is larger than 1 microampere. This is violating this one here. So this is violates this one. So again, this is incorrect assumption. So the assumption is incorrect. So guys, we end up with only one valid assumption, this one here. So this is also incorrect. So we have only one valid assumption now, that D1 is region 2 and D1 in region 1. Okay, and we're gonna solve it now, and I'm gonna show you that this is really works. Okay, and you know, when you train yourself, you will find it, you know, doable. Don't afraid, don't panic. It's just, you know, your first time dealing with diodes, so yeah, you will have some a little bit of panic in the beginning, but as you solve more examples, you will find it, you know, easy enough. So let's take another slide here. Okay, so assume now that D1 in region 2 and D2 in region 1. When I say that D1 in region 2, so ID1 equal to minus 1 microampere, which is minus IS1, which is minus 1 microampere. When I say that D2 is in region 1, that means that ID2 should be less than, as a magnitude, 2 microamperes. Okay, let's go back here and show you. So if D2 is in region 1 here, so the current can be, maximum current is 2 minus 2 micro, as a magnitude, 2 microamperes. So it can be, for example, 1 micro, it can be 1.5 micro, 1.4 micro, 0.9 micro, minus, of course, but it can't be greater than 2 microamperes. Good. So let's see here if we are violating this. So we know that ID1 equal to ID2. So from here, ID2 equal to minus 1 microampere, which is, as a magnitude, less than 2 microampere. So we are still correct, and we will be correct because this is the only you know, remaining assumption. It should be the correct one. Otherwise, you have a problem in your analysis. Okay, let's continue. So ID2 now is 1 microamperes, minus 1 microamperes. So can we get VD2? Yes, we can get. So VD2 equal to, I'm sorry, yeah, VD2 is equal to, you know, guys, you have to convert ID equal to IS e to the power V over VT. You can have to convert. So VD2 is equal to VT ln ID2 over IS2 plus 1. Okay, you plug the number, which is ln minus 1 microamperes here in that relation, and IS is also known. Then you will get your VD. VD from that will be, let's see here, yeah, minus 18 millivolt. And we should wait here for a moment. We know it's reverse. We know that D1 and D2 are reversed. Okay. D2 is reversed in region 1. D1 is reversed in region 2. So we should get negative numbers for the voltages, and that's right. So that's matching the reverse, you know, condition. So we are correct now. We're still correct. Okay, now VD1 from Kirchhoff, from KVL. We know that V input plus VD1 plus VD2 equal to 0. V input is 90. VD1 is unknown for us till this moment. VD2 is minus 18 millivolt, which is 0.018 volt, equal to 0. From here, VD2 will be equal to minus 89.98 volt. Before we continue, D1, I'm sorry, this is D1. D1 is reverse, yes, and the negative sign is valid, is there. So yeah, we are reverse. And it's not breakdown. So VD1 as a magnitude shouldn't be higher than or greater than or equal to 100. And that's the case. So that is negative. So the reverse condition is satisfied. That's also as a magnitude less than 100, which is V breakdown. So we are not in breakdown as we assumed. We assume that D1 is in region 2, not breakdown. Now, you know, the final check that will make everything, you know, match it to each other, you know, to make yourself very satisfied. Now, let's recalculate ID1. So to check, calculate ID1. How we calculate it? We put ID1 equal to IS1, which is 1 microampere, exponential minus 89.98 divided by 0.026 minus 1. If you do that, you will find that in the calculator just equal to 0. So ID1 equal to minus IS1 minus 1 microamperes. Now everything, you know, is in its place. Now the puzzle, you know, is completed. We solve it. Okay. So maybe you say, oh, that's very long. We take maybe 40 minutes in this. No, this is just, you know, an example to show you how to deal with. This is our first example, remember, in reverse. Okay. And this example has 2 diodes. So I am showing you that how to, you know, crack the problem, how to think about it. Okay. How to assume, because forget about solving equations. This is just to show you a method, but in real world, we are not solving equations. We are using our mind. We think about the circuits. We think about the, you know, the givens and try to assume all the time. All the time we guess. We put a good guess, like what we said, and we follow it. If we are lucky, most of the time, that was a good guess, and that's the solution. If you are not unlucky, then we will learn from our guess and, you know, try another one, which would be most of the time or the rest of the time now also the correct one. Okay. Of course, if you guys have you know, if you studied this before, when I solve this equation, this problem, I will just start by this one, because this is basically, you know, there are some information that I didn't tell you, but I will tell now. This should be your first guess from the beginning. Let's see why. So if we go back here, okay, I note 1. This is a basic. This is a basic given. I note 1. 2 givens actually that's really important. First of all, that V input is 90, less than 100, and the diode to go to breakdown, it must have a source that gives him, or, you know, gives it this 100, but the source is only 90. So basically, neither D1 or D2 are in breakdown. They are just reverse. So reverse, either 1 or 2. Okay. If we say that both are in 1, that's also incorrect, because that means that the VD is really small. That means that VD is in millivolts. Okay, and basically if VT is in millivolt, so when we add them together and add them to 90, this will not give us 0, which is KVL. It will be 90 minus, for example, let's say even 1 millivolt, which is much, I'm sorry, let's say even 100 millivolt, which is 4 times larger than VT. So 100 minus 0.1 minus 0.1 will give you 89.8. It's not 0. So one of them is in 2, one of them is in 1. Okay? But ID1 can only have, while now it's not breakdown. So the maximum current is 1 microamperes. It cannot go beyond my 1 microampere. Okay? But ID2 can have 1 microampere, can have more until 2 microamperes. So basically, ID2 will follow ID1 here. It's like if you are walking with your kid, he is just learning how to walk, and you are adult, you can walk, you can speed, you can run, but he can't. So you must, walk with him with his speed. That's what happened here. So ID2, which can carry 1 microampere, minus 1 microampere, or more than 1 minus 1 microampere, like minus 2, okay, must adhere to the requirement or the limitation of diode 1. So both will have 1 microamperes, and under that condition, D1 will be in region 2 and D2 will be in region 1, because if D2 has 1 microampere less than minus 2, it should be something in here. For example, this point. Okay, and that's what happened here. If we look back, we said that if you are in region 1, you should have a voltage comparable to VT. If we go back and see the solution, VD2 is minus 18 millivolt. It's comparable to 26 millivolt, which is VT, right? And why the voltage is small? So that the current is just a portion of 2 microamperes. It should be half of it, which is 1 micro. Okay, guys. I know this was a long example, okay, but again, this is the first one. And as we solve more examples, your hand will become handy. I mean, you will solving such examples will be very doable. Don't worry about that. Okay, so see you in the next video. Bye bye.